Forget what you think you know about life's origins. For a moment, let go of the familiar stories, the settled thoughts. We're about to embark on a mind-bending journey, not just back through the eons of Earth's history, but truly, deeply, into the profound past of the universe itself. Imagine traveling back, not merely to the dawn of our world, but to the very moments when the cosmos began to weave the first threads of existence. Tonight, we will gently uncover whispers from the cosmic dust, whispers that suggest life itself might be an interstellar traveler. We'll explore a radical yet serenely compelling theory, a theory that could softly, gently rewrite the history we thought we knew. This is the quiet work of cosmic archaeology, listening for echoes from beyond, tracing life's earliest interstellar seeds. Settle in, breathe softly, and let your mind drift with the gentle currents of cosmic time. Close your eyes for a moment if you feel comfortable. Imagine our Earth, billions of years ago, a younger, wilder planet bathed in different light, stirred by primeval forces. For a very long time, our understanding of life's genesis, its first gentle breath, has centered on this early Earth. The prevailing theory, often spoken of in hushed scientific tones, is known as abiogenesis. It suggests that life arose spontaneously from non-living matter right here on our home world. Picture it, a warm, shallow pond, perhaps, or a deep sea hydrothermal vent, a soup, a primordial broth, brimming with simple chemical compounds. Under the relentless embrace of lightning strikes, the subtle warmth of volcanic activity, or the slow caress of ultraviolet light from a younger sun, these simple molecules, it is thought, began to dance. They combined slowly, delicately, forming more complex structures. These structures, in turn, might have begun to self-assemble, to replicate, to evolve. A truly remarkable transformation, a quiet miracle unfolding over unimaginable stretches of time on the surface or within the deep fissures of our nascent planet. It is a beautiful theory filled with the promise of emergence from chaos, the spontaneous blossoming of order from disarray. And indeed, laboratory experiments have shown that some of life's most fundamental building blocks, simple amino acids, the very foundations of proteins or nucleobases, the silent architects of DNA and RNA, can indeed form under conditions thought to resemble early Earth. We can recreate the spark in miniature in our carefully controlled environments. We can mix the chemical ingredients, apply the gentle energies, and witness the formation of these foundational components. It's like watching the first delicate notes of a symphony being quietly composed. Imagine the sheer scale of this quiet emergence. From inert minerals, from simple gases, from the very essence of the Earth's early crust, the first flickerings of something resembling life began. A single cell, a microscopic marvel, somehow encased, somehow able to replicate itself, to draw energy from its surroundings, to begin the long, winding lineage that eventually led to all the vibrant, diverse life we see around us today, including you listening to these words. It is a story of profound terrestrial magic, a testament to the potential inherent in the very dust of our planet. Yet, as we consider this elegant narrative, a gentle whisper of wonder, a soft questioning, often arises. The complexity of even the simplest living cell is truly staggering. Imagine a tiny, intricate clockwork mechanism, far more delicate and self-repairing than anything human hands could craft, arising entirely by chance, piece by tiny piece, from a swirling liquid. The jump from simple organic molecules to a self-replicating, self-sustaining entity is a monumental leap a chasm of improbability that sometimes feels too vast for even billions of years to bridge purely by chance. We speak of the primordial soup, a vivid image. Yet what precisely was its recipe? How dense were these vital ingredients? How long did they need to steep and simmer? The conditions on early Earth were volatile, tempestuous. Violent storms, incessant volcanic eruptions, meteor showers scarring the surface. Would such an environment truly nurture the delicate, intricate chemical dance required for life's first stirrings? Or would these nascent molecular structures be torn apart, dissolved, disrupted before they could even begin their grand collaboration? The path from simple building blocks, like those amino acids we can create in a lab, to complex, functional proteins, and then to the even more astonishing structure of DNA or RNA, capable of encoding instructions and self-replicating, is winding and fraught with many, many quiet challenges. It's not just about having the ingredients, it's about having them assemble in precisely the right sequences, in precisely the right configurations, and then having those configurations somehow develop the ability to copy themselves flawlessly and to build the machinery to sustain themselves. It's like having all the letters of the alphabet and then waiting for a complete self-aware novel to write itself simply by the random shuffling of those letters. The precise series of steps, the specific environmental conditions, the precise chemical dance that led to that first fragile spark of life on Earth remains one of the deepest, most beautiful, and most compelling puzzles in all of science. It is a quiet mystery, inviting us to contemplate the profound power of emergence, yes, but also to gently consider if perhaps, just perhaps, there might be other possibilities, other whispers from the deep past. What if that initial spark, that first fundamental seed, didn't arise spontaneously on our young planet alone, but arrived from beyond? What if Earth was it the sole crucible, but merely the receptive soil for a seed that had traveled across the quiet, vast expanses of the cosmos? Let us hold this thought softly as we drift further into the silence. As we delve deeper into the quiet contemplation of life's origins, it's natural to encounter questions that gently nudge at the edges of our understanding. While the terrestrial abiogenesis hypothesis offers a compelling framework, it leaves certain whispers unanswered, certain delicate gaps in the narrative that invite us to look beyond Earth's comfortable boundaries. These aren't criticisms of the theory itself, but rather invitations to broaden our gaze, to expand our sense of wonder. Cool. One of the most persistent and intriguing questions revolves around the chicken or the egg dilemma of life's fundamental components. You see, for life as we know it to function, we need both proteins and nucleic acids. Proteins are the busy workers, the enzymes that catalyze reactions, the structural components that give cells their form. Nucleic acids, like DNA and RNA, are the master blueprints, carrying the instructions for building those very proteins. The challenge is proteins are needed to make DNA and DNA and RNA are needed to make proteins. Which came first in this intricate symbiotic dance? How could one emerge without the other, already being present in some nascent form? Actually, imagine trying to build a complex machine where the tools needed to build the parts are themselves parts of the machine, and the instructions for building the tools are also within the machine. It's a beautifully recursive problem, and it has led scientists to consider simpler, more elegant precursors. The RNA world hypothesis, for example, suggests that RNA, being able to both store information and catalyze reactions like an enzyme, might have been the original molecule of life bridging this gap. But even then, the spontaneous formation of complex, self-replicating RNA strands under primordial conditions still presents a formidable challenge, requiring specific sequences and conditions that are not easily met. It's like finding a perfectly formed, intricate knot without anyone having tied it. Another soft whisper comes from the geological record itself. When we gaze into Earth's most ancient rocks, we find evidence of life appearing remarkably early in our planet's history. The oldest undisputed fossil evidence of life, in the form of microbial mats, dates back approximately Sendern Wu's billion years. Yet, Earth itself only solidified from a molten state around Sendern Wu billion years ago, and for its first few 100 million years, it was a truly tumultuous place, an era often called the Hadean Eon, aptly named for its fiery, hellish condition. Intense asteroid bombardment, widespread volcanism, a searing atmosphere. It seems like a very short window, perhaps only a few 100 million years, for life to spontaneously emerge from scratch, navigate the chicken or the egg problem, and then evolve into something complex enough to leave fossil traces. It's akin to planting a tiny seed in a barren, storm-ravaged landscape and expecting it to blossom into a sturdy tree within a remarkably short growing season. Could life truly have established such a tenacious foothold so quickly amidst such chaos? Or did it arrive, perhaps, already possessing a certain resilience, a pre-existing blueprint, ready to take root in the first available calm? This rapid appearance, often referred to as life early start, hints at an efficiency, or perhaps a pre-preparedness, that some find difficult to reconcile with purely spontaneous terrestrial generation from fundamental inert matter, building blocks themselves. While laboratories can create simple organic molecules under simulated early Earth conditions, the full spectrum of complex molecules found in living systems, the specific chirality of amino acids left-handed versus right-handed versions, the intricate structures of nucleobases, the precise arrangements of lipids, poses additional quiet questions. Why predominantly left-handed amino acids in all terrestrial life? Is this a mere coincidence of Earth's early chemistry, or a subtle clue of an origin elsewhere, where certain chemical preferences might have already been established? It's like discovering that all the bricks in a vast, ancient city were perfectly uniform and wondering if they were all made from the same initial mold rather than being chipped individually from many different sources. The conditions of early Earth, too, present their own quiet paradox. While the primordial soup concept relies on specific environments, perhaps shallow, warm ponds, recent research suggests that early Earth might have been largely oceanic, with a very dense, carbon dioxide-rich atmosphere. The existence of extensive land masses or widespread, stable shallow ponds for the duration needed for abiogenesis is still a topic of gentle debate. Moreover, the constant threat of sterilizing impacts from asteroids and comets during the late heavy dot bombardment era, approximately Sudern E to Sendern Bat billion years ago, raises another soft question. Even if life began, could it have repeatedly survived these global cataclysms only to re-emerge quickly? It's like trying to light a fragile candle in a perpetually tempestuous wind. These unanswered whispers, these gentle nudges from the depths of time and chemistry do not disprove the terrestrial origin of life. Far from it. They simply open a window, a soft aperture, through which we can gaze outwards towards the vast, silent canvas of the cosmos. They invite us to consider an alternative, a complementary narrative. They where Earth might not have been the sole cradle of life's genesis, but perhaps a nurturing harbor, a welcoming destination for seeds that had already begun their timeless journey amongst the stars. It is a thought that expands our understanding of life's potential, stretching it beyond the confines of a single planet, embracing the possibility that we are, in a profound sense, truly children of the cosmos. Let us now drift into this boundless possibility. You know, as we gently drift away from the confines of Earth's early crucible, let us open our minds to a concept as ancient as some of our earliest cosmic ponderings, yet as modern as our latest space missions. This concept is known as panspermia. The word itself comes from Greek roots meaning seeds everywhere. Imagine for a moment that life is not a tender, fragile bloom that must painstakingly begin anew on each habitable world, but rather a tenacious, ubiquitous presence, its fundamental essence scattered throughout the cosmos like microscopic dust motes on a gentle breeze. Panspermia suggests that life's building blocks, or even dormant microbial organisms themselves, might be transported through space from one planetary system to another, or even from one galaxy to another, hitching rides on cosmic vehicles. It's a vision of the universe not as a collection of isolated islands, but as a vast, interconnected ocean where currents of matter and energy gently carry the potential for life across immense distances. This idea is not entirely new. As far back as the 5th century BC, the Greek philosopher Anaxagoras hinted at something similar. In more recent times, in the late Sherjoth and early Erst centuries, figures like Lord Kelvin and Svante Arrhenius quietly championed the concept. Arrhenius, a Swedish chemist and Nobel laureate, proposed radiopanspermia, suggesting that microscopic spores could be propelled across interstellar space by the pressure of starlight. While we now understand that such spores would likely be destroyed by radiation over interstellar distances, the fundamental idea, life traversing the void, had taken root. Today, our understanding of panspermia is more nuanced, more grounded in our growing knowledge of the universe and the remarkable resilience of life itself. We now consider various mechanisms for this cosmic seeding, each with its own quiet elegance. Imagine a violent impact on a distant, life-bearing planet. A colossal asteroid, perhaps, or a comet, slams into its surface with unimaginable force. The impact is so tremendous that it ejects vast quantities of material, rocks, dust, and potentially, within those protective rocky cocoons, dormant microbes, out into space, beyond the gravitational pull of their home world. This is the essence of lithopanspermia, meaning rock seeds. These ejected rocks, now meteorites, embark on a silent, millennia-long journey through the cold, harsh vacuum of space. They might drift aimlessly for millions of years, traveling across the vastness between star systems, until, by chance, their path intersects with another fledgling planetary system, perhaps ours. Consider the gentle descent of one of these cosmic travelers. It might enter Earth's atmosphere, blazing like a fiery messenger, but if it is large enough, its inner core, shielded by the outer layers, could remain relatively cool, preserving any delicate biological cargo. And if it survives the fiery entry, it then quietly, gently lands on the young Earth, potentially delivering its precious payload. We have found meteorites on Earth that originated from Mars. pieces of our neighboring planet ejected by ancient impacts. If rocky debris can travel between planets within our own solar system, what prevents it from traveling between star systems, given enough time and the right gravitational slingshots? The universe is a grand billiard table where celestial bodies are constantly in motion, occasionally colliding, scattering their fragments far and wide. Beyond rocky impacts, imagine other more subtle forms of transport. Perhaps fine dust particles, warmed by a star, gently pick up dormant spores or organic molecules. Or perhaps the very force of stellar winds, those invisible currents flowing from active stars, could carry microscopic particles laden with life's chemical potential outward into the interstellar medium. These are more ethereal forms of panspermia, hinting at a constant, subtle exchange of material across the cosmos. The true beauty of the panspermia concept lies in its vision of the universe as a fertile, interconnected whole. It suggests that the emergence of life might not be an exceedingly rare, singular event confined to isolated planetary oases, but rather a more common, perhaps even inevitable, outcome of cosmic evolution. If life's seeds can travel, then the universe might be quietly, perpetually sowing itself with the potential for biological flourishing. Now, it shifts our perspective from a purely terrestrial beginning, a solitary spark in the void, to a grander, more universal tapestry. It, it weaves Earth not as an isolated experiment, but as one thread in an unimaginably vast, interconnected web of. This deepens our connection to the stars, reminding us that the very essence of life, the fundamental blueprint for existence, might have been forged in distant stellar nurseries, nurtured in interstellar clouds, and then delivered like a precious gift to our waiting world by a gentle rain of cosmic seeds. Let us explore the surprising resilience of these potential travelers. To truly embrace the concept of panspermia, we must gently confront a fundamental question. Could life, even in its simplest forms, truly survive the unimaginable rigors of interstellar travel? The vastness of space is not merely cold and empty. It is a hostile expanse, saturated with destructive radiation, swept by harsh vacuum, and subjected to extreme temperature fluctuations. Could a delicate spark of life, a fragile microbial cell, endure such an odyssey? The answer, surprisingly, is a quiet but firm yes for some forms of life, under certain protective conditions. Our understanding of life's tenacity has grown immensely through the study of what we call extremophiles. These are organisms that don't just survive but actually thrive in environments on Earth that would be instantly fatal to most other forms of life. They are nature's ultimate survivors, quiet masters of endurance. You know, Imagine the deepest parts of the ocean where sunlight never penetrates and hydrothermal vents spew scalding toxic chemicals. Yet, life flourishes there, adapted to crushing pressures and superheated acidic waters. Think of the frozen wastes of Antarctica, where microbes live encased in ancient ice, enduring temperatures that would turn most organisms into brittle fragments. Consider the arid deserts, where life clings to existence in desiccated rocks, or the radioactive waste sites, where certain bacteria demonstrate a remarkable ability to withstand doses of radiation that would obliterate any complex organism. These extremophiles offer us a tantalizing glimpse into life's inherent robustness. For example, consider Deinococcus radiodurans dista, a bacterium often called Conan the bacterium. This remarkable microbe can withstand radiation doses thousands of times higher than what would kill a human, repairing its own DNA with astonishing efficiency. Imagine such a creature, perhaps in a dormant, spore-like state, tucked away within the shielding embrace of a meteorite. The cosmic radiation, though intense, might not be an insurmountable barrier for a truly resilient organism. You know, then there are the tardigrades, often affectionately known as water bears. These microscopic creatures are true titans of survival. They can enter a dehydrated, suspended animation state called a tun, pronounced tune, shriveling up and drawing their limbs inwards. In this state, they can endure temperatures ranging from near absolute zero, the cold of deep space, to well over ebat users degrees Celsius. They can survive extreme pressures, the vacuum of space, and even intense radiation, more than 1,000 times the lethal dose for humans. While tardigrades are complex multicellular organisms and unlikely direct candidates for interstellar seeding, their extraordinary resilience demonstrates the incredible adaptability and survival mechanisms that evolution can bestow upon life, even at microscopic scales. If tardigrades can endure the vacuum of space for days, imagine what a single-celled organism, or a hardy spore, might be capable of over longer durations. Scientists have gone beyond imagination, conducting quiet, careful experiments to test these theories. Microbes have been embedded in artificial meteorites, launched into space, and exposed to the harsh vacuum, cold, and radiation. Some bacterial spores, such as those from Mastbacillus subtilis Paestia, have been shown to survive exposure to the vacuum and extreme cold of space for months, and even years, particularly when shielded by layers of dust or rock. The key often lies in their ability to enter a dormant, dehydrated state where their metabolic processes slow to an almost imperceptible crawl, rendering them far more resistant to environmental stressors. It is like a small seed waiting patiently through a long winter, ready to sprout when the conditions are just right. Furthermore, the journey itself might not always be entirely unprotected. A meteorite provides a natural shield against the worst of the cosmic radiation. The inner core of a meter-sized rock could easily protect microbial passengers from lethal doses of UV radiation and much of the more energetic cosmic rays. The deep cold of space would not necessarily be a killer, but rather a profound preservative, essentially cryogenically freezing the dormant organisms, holding them in a timeless slumber until a warmer, more hospitable environment is encountered. The idea of life as an unyielding traveler, a tenacious seed capable of traversing the cosmic ocean, shifts our perspective on its fundamental nature. It suggests that life is not a fragile accident, easily extinguished, but a powerful, adaptive force possessing an innate drive to persist and spread. It reminds us of the profound strength hidden within the smallest of living things. When we contemplate the silent journey of these potential interstellar pilgrims, our own existence takes on a new, deeper resonance. We might, after all, be the quiet, thriving descendants of these unyielding cosmic travelers, blossoming on a planet that welcomed their ancient, tireless voyage. Let us now consider the vehicles that carry these tiny, tenacious voyagers. If life's tiny, tenacious travelers can indeed endure the vast, quiet depths of space, then what are their cosmic caravans? What are the vehicles that ferry these precious, dormant seeds across unimaginable distances, from one star system to another, perhaps even from a primordial nebula to a nascent planet? The universe, in its boundless elegance, provides an array of silent carriers, each playing a potential role in the grand narrative of panspermia. Imagine first the comets. These ethereal wanderers are often described as dirty snowballs, but they are far more than that. They are pristine remnants from the very dawn of our solar system, icy time capsules preserving the conditions and materials that existed when the sun and planets first formed billions of years ago. Comets spend most of their lives in the frigid, dark outer reaches of the solar system, far beyond Neptune, in regions like the Oort cloud, a vast spherical shell of icy debris, or the Kuiper belt, a disc-shaped region beyond Neptune's orbit. They are like quiet, slumbering giants, waiting for a gravitational nudge to send them on a long, looping journey towards the inner solar system. When a comet approaches the sun, its ice begins to sublimate, creating a beautiful glowing coma and a spectacular tail. But beneath this ephemeral beauty, the comet holds a treasure trove of potential. We have discovered that comets are rich in water ice, yes, but also in complex organic molecules, the very building blocks of life, such as amino acids, sugars, and alcohols. These aren't simple inert chemicals. They are the fundamental components from which life on Earth is constructed. Imagine if, within these icy matrices, protected from radiation by layers of ice and dust, dormant microbial spores were also encased, preserved in a deep freeze for eons. A comet then becomes a slow, deliberate spacecraft, a natural biological vehicle, delivering both the essential water and the foundational organic ingredients, along with any hidden passengers, to a newly forming planet. It's like a cosmic delivery service, bringing the very ingredients for a garden and perhaps even its seeds to a waiting world. Next, consider the asteroids. These rocky wanderers, predominantly found in the asteroid belt between Mars and Jupiter, are different from comets. They are generally rockier, less icy, but like comets, they can be ejected from planetary systems through violent collisions. We know that significant impacts can send chunks of planetary crust hurtling into space. As we discussed, these meteorites can then travel through the void. If a planet were to harbor life, even primitive microbial life, a colossal impact event could launch these life-bearing rocks far beyond their home system. Imagine a collision on a distant, already living world. The force is immense, ejecting millions of tons of material. Some of these fragments achieve escape velocity, becoming interstellar meteorites. They travel for millions of years, sometimes billions, traversing the silent, star-strewn distances. The journey is long, but the cold vacuum of space is an excellent preservative. When one of these rocky fragments, perhaps only a few meters wide, eventually encounters a new planetary system, it might be captured by the gravitational pull of a young planet like Earth. Its fiery entry through the atmosphere would burn away much of its outer layers, but a small, shielded interior could survive, gently delivering its ancient, dormant cargo to the surface. It's like a message in a bottle, cast into a vast cosmic ocean, waiting for an unknown shore. Beyond these larger bodies, consider the almost imperceptible cosmic dust grains. These microscopic particles, often mere micrometers across, are ubiquitous throughout the universe. They are formed in the atmospheres of old dying stars, or in the vast cold clouds between stars. And importantly, these dust grains are known to be sites of complex chemical reactions where simple atoms can combine to form surprisingly intricate organic molecules. Imagine if, on the surface of these tiny cosmic motes, or perhaps encapsulated within their porous structures. Dormant spores or even free floating viruses could hitch a ride. While the journey would be less protected, the sheer abundance of cosmic dust and the fact that it is gently pushed by stellar winds and radiation pressure means that it could be a constant, subtle drizzle of potential biological material across the cosmos. This would be a form of radiopanspermia that is more plausible than Irenaeus's original hypothesis, involving much smaller, more resilient particles. The universe in this vision is not static and segmented, but dynamic and interconnected. It is a grand cosmic exchange system where matter, energy, and potentially the very seeds of life are constantly in motion. These cosmic caravans, the silent, majestic comets, the enduring rocky asteroids, and the ubiquitous microscopic dust grains are not merely inert objects. They are the potential carriers of life's story, weaving a profound narrative of universal connection. They suggest that the universe itself might be a gardener, constantly scattering seeds across its boundless fields, waiting for them to take root in fertile soil. And perhaps our beautiful Earth was one such field, quietly receptive to an ancient cosmic rain. With this expanded, let us now search for the subtle imprints of these interstellar travelers within the very fabric of our world and beyond. As we continue our quiet exploration, let us now turn our gaze towards the Earth itself, seeking the subtle whispers and enduring imprints that might suggest an interstellar heritage. If life seeds indeed arrived from the cosmos, they would have left traces, echoes within the ancient rocks and the very chemical fabric of our planet. This is the painstaking, meticulous work of cosmic archaeology on Earth, searching for clues left by visitors from beyond. Okay, imagine yourself as a geological detective, sifting through layers of time preserved in stone, one of the most compelling pieces of evidence for life's early presence, and therefore a potential indicator for a rapid emergence or arrival, comes from what we call ancient microbial fossils. The oldest undisputed evidence of life on Earth comes from stromatolites, layered rock structures formed by the growth of ancient microbial mats, primarily cyanobacteria. These silent witnesses date back approximately 7 billion years, found in places like Western Australia. To find such complex organized microbial communities so early in Earth's history, after a period of intense bombardment and geological upheaval, sparks the quiet question: how did life become so established so quickly? These fossils don't definitively prove panspermia, uh, but they do highlight the remarkably swift appearance of complex life forms on a relatively young planet. Beyond visible fossils, scientists search for more subtle chemical signatures of ancient life. One powerful tool in this cosmic archaeology is the study of isotopes, particularly those of carbon. Carbon, the very backbone of all known life, exists in several forms, or isotopes, differing slightly in their atomic weight. The most common are carbon-styrran, carbon-sursan. Living organisms, through their metabolic processes, have a subtle but distinct preference for the lighter carbon-styrran. This means that biological processes tend to incorporate more carbon-styrran into their structures, leaving behind a slightly higher proportion of carbon-sursan in the surrounding environment, right? So when geologists examine ancient rocks, particularly those thought to contain remnants of early organic matter, they carefully measure the ratio of carbon-styrran to carbon-sursan. If they find a signature of enrichment in carbon-styrran that is characteristic of biological activity, even in the absence of obvious fossils, It tests a powerful whisper of ancient life. Such isotopic anomalies have been found in rocks dating back nearly 7 billion years in Greenland, extending the potential timeline for life's presence on Earth even further back. To find such subtle, indelible biological fingerprints etched into rocks from a time when Earth was still cooling from its fiery birth reinforces the idea of life's incredibly early and perhaps robust establishment, but the most direct, tangible evidence of extraterrestrial organic delivery comes from our careful study of meteorites. These are the very cosmic travelers we discussed, but fragments of asteroids and comets that have survived their fiery descent through Earth's atmosphere and landed upon our planet. For decades, scientists have meticulously analyzed their composition, and what they have found is truly astonishing. Consider the Murchison meteorite, which fell in Australia in Ichen Jubite Loser Jolt. This ancient visitor from space, a carbonaceous chondrite, was found to contain over different amino acids. Think about that for a moment. The fundamental building blocks of proteins, the very machinery of life, delivered directly from space. And not just a few types, but a rich diversity. Crucially, some of these amino acids are rare or non-existent on Earth, suggesting a distinct extraterrestrial origin. Furthermore, the Murchison meteorite, and others like it, contained nucleobases, the components of DNA and RNA, and even sugars, all complex organic molecules crucial for life. And what is particularly intriguing is that many of these extraterrestrial amino acids exhibit what is called a racemic mixture, meaning they have roughly equal amounts of left-handed and right-handed forms. Terrestrial life, however, almost exclusively uses left-handed amino acids. While this difference might seem to argue against direct seeding of fixed organisms, it strongly supports the idea of a constant, gentle delivery of life sus ingredients from space. It's like finding a cosmic pantry, stocked with all the raw materials needed to bake a cake long before the oven on Earth was even hot enough. These geological and isotopic clues, combined with the chemical analysis of meteorites, paint a compelling picture. They suggest that early Earth was not an isolated chemical experiment, but rather a planet constantly receiving gifts from the cosmos. A gentle, persistent rain of organic molecules, carbon, and perhaps even microscopic seeds delivered by comets and asteroids, enriching the primordial environment and potentially giving life a crucial head start. It's a vision of our planet as a cosmic recipient, ready to nurture the potential carried within these ancient travelers. As we reflect on these earthly whispers, let us now turn our gaze outward to the vast cosmic laboratories where these very ingredients are formed. As our quiet journey continues, let us lift our gaze from the ancient rocks of Earth and extend our senses outwards into the deep, silent expanse of space itself. For the universe, it turns out, is not merely a dark void, but a vast, shimmering chemical laboratory where the fundamental ingredients of life are not only present but actively forming, swirling within gigantic clouds of gas and dust. Our astronomical instruments, acting as patient stardust sentinels, are listening, observing, and revealing this cosmic chemistry to us, a silent symphony of creation playing out across light years. Imagine peering into the heart of a vast nebula, a breathtaking cloud of gas and dust, thousands of light years across. These nebulae are the cosmic nurseries where new stars and planetary systems are born. For many years, we thought of them simply as reservoirs of hydrogen and helium, the basic building blocks of stars. But with the advent of powerful radio telescopes, we have discovered a far richer, more complex reality. These telescopes, listening to the faint radio waves emitted by molecules, have become our quiet ears, picking up whispers of chemistry unfolding in the cold, dark depths of space. And what have these stardust sentinels revealed? A veritable molecular wonderland. We have detected, with increasing precision, the presence of surprisingly complex organic molecules within these interstellar clouds. When we're talking about molecules like alcohols, including ethanol, the alcohol in beverages, aldehydes, ketones, and even more intricate structures. More astonishingly, astronomers have identified simpler amino acids, like glycine, and various types of sugars in these cosmic clouds. These are not just theoretical, these are direct observations of the very raw materials of life, floating freely in the vastness between stars long before any planet has even begun to coalesce. Think of a primordial cosmic soup, not confined to Earth's early ponds, but spread across light years, simmering gently under the influence of diffuse starlight and cosmic rays. These complex molecules form on the surfaces of tiny dust grains within these nebulae, acting as miniature catalytic factories. When hydrogen atoms, carbon atoms, oxygen, and nitrogen collide and stick to these cold dust grains, they can react and combine, slowly building up more complex structures shielded from the harshest radiation by the dust itself. It's a slow, quiet molecular dance, played out over millions of years, creating the foundational building blocks of life in the deepest cosmic silence. Beyond interstellar clouds, our robotic emissaries have ventured closer, directly sampling the chemical makeup of comets. The Rosetta mission, for example, which orbited and landed a probe on comet Lukshaty P. Churyumov-Gerasimenko, sent back invaluable data. It confirmed that comets are indeed rich in water, but also in a wide array of organic molecules, including a significant number of different amino acids. The Stardust mission, another quiet cosmic explorer, actually flew through the coma of comet wild Ariane collected dust grains, bringing them back to Earth for analysis. These grains, too, were found to contain glycine, the simplest amino acid, directly from a comet. These findings are they tell us that the universe is not waiting for life to emerge on a planet. It is actively, quietly preparing the ingredients for life everywhere. The building blocks are not unique to Earth. They are pervasive throughout. When new planetary systems form within these nebulae, these nascent planets are not barren, inert worlds. They are born into an environment already rich with the potential for life. The comets and asteroids that subsequently rain down on these young planets are not just bringing water and rock, they are delivering a sophisticated chemical toolkit, a gentle cascade of life's very essence from the depths of interstellar space. You know, this grand cosmic preparation suggests a profound truth. The universe itself seems inherently hospitable to the genesis of life's fundamental chemistry. It is like a master chef, meticulously preparing all the ingredients, chopping the vegetables, grinding the spices, kneading the dough, long before the final dish is assembled. The Earth, then, might not have been a lone, isolated kitchen where life was conjured from scratch, but rather a perfectly warmed oven into which all the exquisitely prepared cosmic ingredients were gently placed, ready to bake into the vibrant tapestry of existence we see today. Let us now delve deeper into how these cosmic ingredients might have influenced life's very first steps on our world. With the quiet understanding that the cosmos is brimming with life's essential ingredients, let us now revisit the concept of the primordial soup on early Earth, but this time with a profound interest. The traditional view often implied that all the necessary chemistry for life's origin had to spontaneously arise on pied Earth. But what if, instead, Earth received a continuous gentle rain of preformed organic molecules from space, kick-starting and accelerating the process? What if the universe provided a sophisticated, ready-made recipe rather than forcing Earth to invent every step from scratch? Imagine the early Earth still in its tumultuous youth, but slowly cooling, its oceans forming. Instead of waiting for lightning strikes and volcanic vents to painstakingly synthesize every single amino acid or nucleobase, picture a steady delivered by the thousands of comets and asteroids that were still impacting our young planet. Each impact, instead of being purely destructive, could also have been a delivery service, but enriching Earth's nascent waters with a diverse and abundant supply of life's building blocks. This would fundamentally change the challenge of abiogenesis. It transforms the problem from synthesizing everything from scratch in a chaotic environment to merely organizing and refining pre-existing complex components. It's like being given a large box of exquisite pre-cut puzzle pieces rather than having to find the raw materials, cut each piece, and then try to fit them together. The sheer quantity and diversity of extraterrestrial organic molecules detected in meteorites and comets suggests that early Earth was not lacking in these crucial ingredients. Consider the role of prebiotic chemistry in space. We've touched upon how complex organic molecules form on cosmic dust grains in nebulae. These aren't just simple molecules. Some are surprisingly intricate, containing dozens of atoms. The conditions in interstellar space, extreme cold, vacuum, and the presence of cosmic rays, might seem inimical to chemistry, but in fact, they provide a unique environment. On the surface of dust grains, atoms and simple molecules can stick, unable to escape, slowly accumulating and reacting over vast timescales. This process, undisturbed by the churning of a planetary atmosphere or the violence of a boiling ocean, can lead to the formation of highly specific and organized molecular structures. The RNA world hypothesis, as we gently discussed earlier, posits that RNA, capable of both storing genetic information and acting as an enzyme, might have been life's original molecule. But forming complex, self-replicating RNA strands from simple precursors is still a significant chemical hurdle. What if, however, the very precursors of RNA, the nucleobases adenine, guanine, cytosine, uracil, and even parts of the sugar phosphate backbone, were delivered from space? We know meteorites contain nucleobases. If these crucial components were already present in abundance on early Earth, thanks to cosmic delivery, the path to an RNA world becomes significantly less steep. It's like being handed the perfect threads, colors, and needles, making the weaving of the tapestry much more feasible. This idea of an interstellar recipe shifts the location of some of the earliest, most difficult steps of life's chemistry from Earth to the vast cosmic expanse. It implies that the universe itself performs a significant amount of the preparatory work. The Earth then becomes the perfect incubator, the final assembly line, where these pre-processed ingredients, having traveled for millions of years, can finally combine and coalesce into the miracle of a self-replicating system. Think of it as a cosmic relay race. The first leg, the synthesis of fundamental organic molecules, happens in interstellar clouds and on comets and asteroids. The second leg, the delivery of these molecules to a habitable planet, is carried out by impacts. The final leg, the precise arrangement and self-assembly into living systems, takes place on the planet itself. This cooperative model, where Earth benefits from the universe's pervasive chemistry, offers a more elegant and perhaps more probable pathway for life's rapid appearance. It softens the demanding expectation that all the intricate steps of abiogenesis had to occur solely within Earth's limited early environments. Instead, it weaves a narrative of universal collaboration, where the cosmos provides the raw materials, the basic tools, and perhaps even some partially assembled components, allowing life to blossom more readily on fertile worlds. This vision deepens our sense of connection to the stars, suggesting that our very biochemical fabric might carry the faint echoes of its extraterrestrial birth. It invites us to ponder if life's chemistry is so pervasive and its seeds so tenacious. What does this imply for our place in the grand cosmic family? Let us gently explore this profound question next. As our quiet journey nears its contemplative close, we arrive at a profound reflection. What does it truly mean if life, in its fundamental essence, originated not just on Earth, but was seeded from the cosmos? What are the implications of embracing a cosmic lineage, of acknowledging that we might all be, in a very real sense, cosmic descendants? Firstly, and perhaps most beautifully, it deepens our connection to the entire universe. If life's building blocks, or even its earliest microscopic forms, traveled across interstellar space to reach our planet, then the very atoms that make up our bodies, the very processes that allow us to live and breathe and think, carry an echo of a journey far grander than we ever imagined. We are not merely children of Earth. We are children of the stars, born from dust that traveled untold light years, nurtured by cosmic processes that span galaxies. This understanding infuses our existence with an even greater sense of wonder and belonging within the vast, interconnected tapestry. It reminds us that we are not isolated, but intimately intertwined with the grand flow of cosmic evolution. Secondly, the concept of widespread interstellar seeding significantly increases the odds of finding life elsewhere in the universe. If life can not only arise, but also travel and take root on other planets, then the universe might be far more biologically active than previously thought. Instead of life being a rare, spontaneous fluke that must originate independently on each habitable world, it becomes a potentially common occurrence, a universal pattern. This shifts our search for extraterrestrial life from looking for isolated, fragile sparks to seeking out blossoms in a widespread cosmic garden. It suggests that if the conditions are right, if a planet has liquid water, a stable energy source, and a protective atmosphere, life, in some form, might be waiting to take hold, or may have already arrived from the silent, endless cosmic rain. Imagine the quiet implications. If life can travel, then perhaps all life in a given region of the galaxy shares a common ancient ancestor. We might not be merely distant cousins to potential life on Europa or Enceladus, but direct biological relatives sharing the same primeval cosmic lineage. This vision hints at a profound biological unity across the stars, suggesting that the basic blueprints for life might be universally shared, adapting and evolving in countless unique ways on countless unique worlds. It's like discovering that all the diverse trees in a vast forest grew from the same original seed type, subtly shaped by their varied environments. Of course, embracing this cosmic lineage also prompts new questions and invigorates future explorations. The search for life elsewhere becomes even more compelling. Our current astrobiology missions and those planned for the future are pushing the boundaries of what we can discover. Quite consider the James Webb Space Telescope, JWST. While not directly searching for microbes, its incredible sensitivity allows it to analyze the atmospheres of exoplanets, planets orbiting other stars. By looking for specific chemical signatures like oxygen, methane, or ozone in these distant atmospheres, the JWST can identify potential biosignatures, chemical indicators that might suggest the presence of life. If we detect such signatures on multiple exoplanets, especially those around older star systems that might have ejected life-bearing material, it would provide further tantalizing evidence for the prevalence of life's ingredients, and perhaps even life itself throughout the galaxy. No, future missions are even more direct in their search. The Europa Clipper, for example, is destined to explore Europa, a moon of Jupiter, which is believed to harbor a vast subsurface ocean beneath its icy crust. The Dragonfly mission will send a drone-like lander to Titan, Saturn's largest moon, with its dense atmosphere and liquid methane lakes. While these missions seek indigenous life, their findings about the resilience of life in extreme environments or the prevalence of organic chemistry in the outer solar system will further inform our understanding of panspermia. They are quiet reconnaissance missions, seeking the hidden corners where life might be patiently waiting. You know, the concept of cosmic archaeology, tracing life's earliest interstellar seeds, is a journey without end. It invites us to remain open, curious, and profoundly connected to the unfolding story of the universe. It encourages us to look not just down at the soil beneath our feet for life's origins, but up to the boundless, star-strewn canvas that has always been our silent home. It reminds us that the universe is not just a stage for life, but perhaps, in its gentle, pervasive way, a quiet, ancient gardener, forever sowing the seeds of existence across the vastness of time and space. As we conclude this exploration, let us carry this expansive thought with us. Our origins, our very essence, might be woven from threads that stretch across the cosmos, connecting us to every star, every nebula, every silent ancient wanderer. It is a peaceful, humbling thought, inviting us to embrace our true, magnificent cosmic lineage